We are very honored today to have Thérèse Encrenaz and Rakesh Mogul with us to speak about their latest research regarding Venus. More in particular, what happens or what not happens in and around the clouds of Venus. Thérèse Encrenaz will speak first. Thérèse is a planetary scientist and emeritus scientist at the Paris Observatory in France. She's a specialist in planetary atmospheres, has been involved in many planetary missions and cometary missions, for example, Vega, Galileo, Mars Express, Venus Express, Rosetta, and more. And she has been involved, and we will hear about that today, in a lot of ground-based observing campaigns at Mauna Kea Observatory in Hawaii, but also at European Southern Observatory in Chile. She's the author of a large number of research papers and popular books about the solar system and planetary science. Rakesh Mogul is a professor in the Chemistry and Biochemistry department at the California State Polytechnic University, which is located in Pomona. If you don't know where that is about 30 minutes drive east out of Los Angeles. Rakesh teaches biochemistry. He used to teach organic chemistry as well, so he's really very good with everything chemical. His research spans planetary science, astrobiology regarding Venus, analytical biochemistry, and molecular microbiology. So without further ado, I will give the floor now to Thérèse, and I will share my screen so that because I have Thérèse's slides. So let's see if I do that. Can everybody see that? Yeah? All right. Thérèse, the floor is yours.
Okay. Thank you, Martin. Thank you for inviting me. It's a pleasure to be here. So I'm going to report on a observing campaign we have been doing since 2012 at Mauna Kea Observatory. Next slide, please. We have been using an imaging spectrometer working the thermal infrared, which is called TEXS. It allows to make maps of minor species using the right spectral range. So our objective was to better understand the SO2 and water cycles above and within the clouds. And to do that, we have been observing at various wavelengths. We choose the three bands of SO2 at 7.4, 8.9, and 8.6 micron. And by the way, we also got a transition of HDO, which gave us access to H2O at 7.4 micron. So we had 27 campaigns since January 2012. And what you see below are three examples of spectra. On the left, you see the interval at 8.6 micron that we have been observing only recently. And the two other ranges at 7.3 and 19 micron, we have monitored them all over the decade. Next slide, please. In addition, we had other objectives. We were able to analyze the thermal profile using the CO2 bands, especially strong and weak lines in various bands. And this actually has been the job of Rohini Guides, which has used one of the bands and has inverted the thermal spectrum. This has been published in 2022. And we have used our database to search for minor species and to retrieve upper limits. And I will talk about that at the end of the talk. Thank you. Next slide. Okay. Now about the data analysis. It's a very simple analysis. It's a quick look analysis, I would say. We take lines, weak lines of SO2, HDO, and CO2, and we simply make the ratio of the line depth to get an estimate of the mixing ratio. So you see here on the right, you see the spectrum we have at 7.3 micron. In the case of HDO, we infer H2O using a given value for the D over H ratio. And if you look at the spectrum, you see that depending of the runs, the SO2 line is changes very much in intensity, while the CO2 line is about always the same. So just at first glance, you can see this is the disk integrated spectrum. You can just see what is the level of abundance of SO2. And as you will see, it varies very strongly. Next slide. An important question is where the radiation comes from. The advantage of having three spectral ranges is that you probe different altitude levels. And this is because the H2SO4 extinction coefficient is strongly varying over the thermal infrared range. So you see that at 8.6 microns, that's the red arrow, you probe at about 67 kilometers, while at 1355 centimeter minus 1, you are a little below 62 kilometers. This is what we call the cloud top in our model. And at 530 centimeter minus 1, that's the blue arrow, you see that we are at 57 kilometers. So we get information about the variations of SO2 over altitude. Next slide, please. Okay. We very immediately we realized that SO2 and water maps were extremely different. The water maps, so you have an example on the right, the HDO lines actually, they're extremely homogeneous. And in addition, the variations of the disk integrated mixing ratio shows moderate variations as a function of time over the whole decade. In contrast, the SO2 maps are extremely patchy. They show plumes which appear and disappear at a time scale of a couple of hours sometimes. And what you can see also is that in a given run, that's to say 8 hours, you can see the plume which follows the 4-day rotation at the cloud level. And in addition, we see very strong variation, long-term variation of the SO2 abundance. This is shown on the next slide. This is the complete data set since 2012 up to now. At the top, you have the H2O, that's the disk integrated mixing ratio in ppm. And below in red, you have the SO2 mixing ratio. And in addition, we have plotted the sunspot number, which gives you an indicate of the solar activity, the UV radiation. And it appears that you have a good correlation between this curve, solar excitation, solar irradiation, solar activity, and water from the beginning until 2022, something like that. And if you look at SO2, you see that between 2014 and 2023, you see a nice anticorrelation with H2O. And this can be explained by the influence of photochemistry, because photochemistry is driven by the UV solar flux. And if you have higher solar activity, the photochemistry will be more active and SO2 will be depleted. And also the photochemical model predicts that you may have an anticorrelation between SO2 and H2O in this case. So until 2023, we have a reasonable explanation for what we see. But after 2023, you see that things become very different. We have increase and decrease of SO2 by a factor as much as 5 on a time scale as short as 2 months. And this cannot at all be explained by the solar activity. So this is actually the big open question which is raised by this data. Next slide, please. So we wondered whether this mechanism could have been observed in the past. So you see here all the record from Pioneer Venus up to now, with, again, the solar cycle in yellow. And you see that at the early beginning, around 1980, indeed, you have a strong decrease of SO2, which might be due to the solar cycle, which was at its maximum. But it's no more true after. You see that after 85 until 1990, this correlation doesn't appear at all. And if you go to Venus Express, you see that it's not true either, because Venus Express in 2006, we started with a big decrease, which was at a time where the solar activity was minimum. So again, in this case, photochemistry cannot explain what we see. Next slide. So to try to understand what happened after 2023, we have plotted here all the possible parameters which might be involved. You see in red the Venus diameter, which tells you whether we see the night side or the day side. You see the local time in black, and you see the longitude in blue. And it's not clear what happens, except that might be a trend for SO2 to be maximum when the diameter is large. That's to say, when we are looking at the night side. So we wondered if this was really the case. So next slide, we went back in the past, but then you see it's no more true, because look at what happens in 2022. At that time, the SO2 abundance is very low, as it's minimum, typically, and still we are looking at the night side. So what we see after 2023 is not true before, and again, this pleads in favor of a change of regime appearing around 2023, but we don't know what it is. Next slide, thank you. Now we come to what is new. That's the first detection of the third band of SO2 at 8.6 micron. Here we are above at 67 kilometers, and in addition, the band is intrinsically weak, so it's difficult to detect. And actually, we didn't detect it before 2023. And we have followed in the following runs, we detected this band only when the abundance at 62 kilometers is above 400 ppb. If it's lower, we don't see it. Next slide, please. So this is an example of what we see in July 2023. So for the maps, for the middle and the right, we do, as I said, we do the ratio of SO2 line depth by CO2 line depth. But unfortunately, we cannot do that at 67 kilometers because this new band, this new interval, has no CO2 transition. So we are model dependent about to determine the mixing ratio. So what you see below are two examples of spectra in which we have tried to fit the data as best as we could. I must say that this is very simple. We have no forward model for radiative. We have only a forward model for radiative transfer. We have no automatic retrieval. So this is an example of a reasonable fit, but it is by no way unique. So in this case, if we have 500 ppb at 57, 400 ppb at 62, then we fit the spectra with something like 100 or 150 ppb at 67 kilometers. Next slide, please. I wanted to show you this because it's a nice example. It's an exceptional situation where we see a dynamical structure lasting for 5 days. I told you that the plumes are usually with a time scale of about a few hours, always less than a day. But this time we have a very peculiar structure. We have two latitudinal bands at plus and minus 30 degrees, while usually, I should have told you, usually the plumes appear preferentially at the equator. But in this case, we have this strong dynamical structure which lasts for 5 days. And that's something which is really exceptional. You can note that on the right, you have a map of the continuum at 62 kilometers, and you see a sort of diurnal wave, a maximum of the temperature on the first day and on the last day. So that may be the presence of a thermal wave. Okay, next slide. Now we looked at what happens between 57 and 62 kilometers. And for that, we did the ratio of the abundance at 57 divided by the abundance of SO2 at 62. And you see that in most of the cases, we have a value which is around 1.5. And that makes sense because we know that SO2 is depleted when the altitude increases. But you see some exception, which also we don't understand. Look at 2018. There is a very sharp decrease of the SO2, and it's the same in 2022, which was at a time of a very strong plume activity. And even more surprising, we see the opposite as well. If you look at what happens after 2021, we have several occasions where the mixing ratio at 57 kilometers seems to be lower than the one of 62, which is really a surprise. So I have absolutely no explanation for all this, but I think all these data deserve better understanding. Thank you. Next slide, please. So to summarize this part of the discussion, we clearly have a change of regime around 2023, with photochemistry being able to account for the data before and some new mechanism taking place after. And what could be this mechanism? Thermal tides, but we see no clear correlation with local time or longitude. Is there a conversion mechanism between SO2 and aerosols? This will be the topic of the whole discussion today. In fact, we know that most of the SO2 below the cloud is much more abundant than above. And H2SO2 alone cannot account for all this SO2. So there must be a storage of sulfur somewhere. And this is really an open question. And maybe what we see is a conversion mechanism. So what could be the case for that? Possibly a change in temperature, if it's a condensation effect. Martin recently published a paper showing some possible correlation between the temperature and the UV radiation. So maybe it's a way to go, or thermal tides, convective activity. So that's the end of this part. And now I will, next slide, please. I will discuss very briefly the upper limits we got. In fact, this study was motivated by the announcement by Jane Grieve of possible phosphine from millimeter heterodyne spectroscopy measurements. And also there was a paper by Rakesh announcing the possible detection of various minor species. So we used our database to see whether we could bring something to this discussion, knowing that at the same time we had upper limits from the solar occultation experiment of Venus Express by Trompé and by Mailleux and colleagues. So we have been using Texas data we have looked for pH3 at 62 kilometers at 950 centimeter minus 1, NH3 at the same wavelength, also at 62, and HCN at 747 centimeter minus 1, and this probes a little deeper, around 57 kilometers. Next slide. So these are the two upper limits we got for pH3 at 955 centimeter minus 1. In both cases, we see no evidence for a local source, nor for a diurnal variation. Next slide. This is NH3, same conclusion. The upper limit of NH3 is very good because the band, the line is very strong. And finally, HCN, next slide, also shares a very good upper limit. So conclusion, I think, yeah. For pH3, a comment about pH3. We observed so far afternoon and night side. And the suggestion by Jane Greaves was that we might have more pH3 at the morning than at the evening. So I was thinking that we could repeat the observation if we are able to get the morning side, and we could probably also get a better upper limit. In the case of NH3, we are consistent with the solar occultation measurements. And in fact, and with HCN, we improve this factor. So that's what I had to report, and thank you for your attention. Thank you.
Thank you. Thank you very much, Thérèse. That is so perfectly within your timing also. Okay, let's go straight to the next talk.
Okay, great. So the abbreviated title for my talk is Venus's Clouds Aerosols Contain Abundant Water and Iron. This work was recently published in JGR Planets. And before I start, I want to give a shout out to my colleagues, Zolotov, Wei, and LeMay, who are co-authors on this work. So this work is about measures obtained from the Pioneer Venus Large Probe. The Large Probe separated from the Pioneer Venus Multiprobe in 1978. And then in December that year, the Large Probe descended into Venus's increasingly hot atmosphere and impacted the surface after about a 54-minute descent time. On board the Large Probe were several instruments, two of which were the Large Probe Neutral Mass Spectrometer and the Large Probe Gas Chromatograph, and both of these instruments measured atmospheric gas abundances throughout the descent. This talk is really about the Large Probe Neutral Mass Spectrometer. This instrument was also known as the LNMS, and this was an electron ionization mass spectrometer that operated at three different electron ionization energies, 70, 30, and 22 eV. And in essence, the LNMS collected 45 spectra, and the spectral acquisition started at 64 kilometers in the atmosphere. So a little bit near where Therese's work is, but really most of the data was obtained much below that. So what's really central to this talk is that the LNMS experienced a significant, though temporary, clog of the inlets between 50 and 25 kilometers. But then at 25 kilometers, the clog cleared out and nominal intake resumed. Now, evidence for this clog is really nicely seen in the LMS CO2 profile, where CO2 is the most dominant gas in the atmosphere. And what we see here is a 6,000-fold decrease in CO2 abundances between 50 and 25 kilometers. And this is attributed to the inadvertent capture of aerosols from the clouds and the subsequent decomposition of the aerosols in the atmosphere, the hot atmosphere below the clouds. So this sequence of events of aerosol capture and subsequent thermal decomposition are better shown in this slide, where I have a cartoon drawing for these steps. So on the left is a schematic of the LNMS instrument, which was on the inside of the probe, but this instrument had a couple of inlets that stuck out into the atmosphere. And these inlets had a very small opening of about 0.1 microns or less. So as the Large Probe dropped through the clouds, especially between 51 and 48 kilometers, several aerosols were captured. And these aerosols are captured on and inside the inlets. And this is what caused the big drop in CO2 abundances. But then as the Large Probe descended deeper in the atmosphere between 50 and 25 kilometers, the inlets began to heat up because atmospheric temperatures also were going up. So as a result, the aerosols began to thermally decompose and release gases such as SO2, water, and O2. And then these gases were used to deduce the aerosol composition. So this assessment was originally published in 1980 by the original LMS investigators, and then we confirmed this analysis through our reanalysis of the LMS data in 2023. But in our reanalysis of the data, we realized that this assessment was actually somewhat incomplete. And what we propose is that, yes, the decomposition occurred, but there were remnants of the aerosols that remained in the inlets. And then that's these pink dots over here. Then as the instrument or as the probe dropped deeper in the atmosphere below 25 kilometers, where atmospheric temperatures really go up, the decomposition continued and other compounds were released and measured by the LNMS. So in other words, what we've been saying is that the LNMS data, which was archived at a NASA facility and sat there for about 45 plus years, actually contains a lot of uncharacterized data that relate to aerosol composition. And we were able to extract this information and then propose a new aerosol composition. So the first thing I want to present are these apparent mixing ratios for SO2 and water that we pulled from the LNMS data. And we pulled this using methods that we developed for the LNMS, and we published in Icarus and Methods X in 2023. So on the left is SO2, which is a very, very funky profile with one major peak at 35 and another major peak at about 10 kilometers. So very odd. So here are the measurements in comparison obtained by the gas chromatograph on the large probe. So a different instrument, but on the same exact space probe. So these values are not exactly the same, but they're within the uncertainty limits. And now here's where things get weird. Here's our measurements obtained by radio occultation, near-infrared spectroscopy, gas chromatography below the clouds by Venera 12, and UV spectrometry in Vega 1 and 2. And note that this plot uses the log scale. So in other words, the LMS values and in part the LGC values are very high compared to all other measurements. So this is the first indication that whatever the LMS and in part the LGC measured was something weird, something else was going on. And then is the water profile from the LMS. This water profile has the same exact shape as the SO2 profile, a major peak at 35 and a major peak at around 10 kilometers. So here are the measurements, and let me back up. Again, this is on a log scale, which becomes important in a moment. So here are the measurements from the LGC. Again, a different instrument, but the same exact probe. So these values are almost identical. So this is actually good news for us that what we're doing here is actually somewhat calibrated by the LGC measurements. However, all spectroscopic measurements, near-infrared spectroscopy and optical spectroscopy, indicate that water vapor should be about 30 ppm. Now, considering this is a log scale, this is a massive, massive difference. So something weird is going on. So me and Sanjay and Mike as well, and I believe Misha as well, what we saw here was basically a dividing line, that indirect measurements by spectroscopy or light-based measurements yielded low water, but these instruments, the LGC and LMS, actually directly sampled in the clouds and got high water values. Similarly, all these measurements obtained by the moisture meter on Vega 2, the GC on Venera 13 and 14, and the hygrometer also on Venera 13, 14, these instruments also directly sampled in the clouds and also measured high abundances of water. So we saw a nice dividing line here, that indirect measurements using light got low water, but any direct sampling that went through the clouds and directly sampled in the clouds received high water. So once again, some very, very interesting results. So how was this explained? So in the original LMS investigations, some of these trends were explained by the capture of some aerosols containing sulfuric acid. In that, yes, aerosols were captured, but then these aerosols began to thermally decompose and release SO2 and water, as indicated by these bumps in the yellow box. However, in these original LMS investigations, this second bump of SO2 was left unexplained, and this large bump in water was attributed to terrestrial contamination or earth water. So in other words, Venus water was measured first, and then later Earth water was measured. And then moreover, this water way up top across several different publications, as far as we can tell, these high abundance of water have been attributed to instrument artifacts or bad design of instruments. So we looked at this and said, well, maybe there's a much more simpler explanation for all of this data. So what we've proposed is that this is the result of capture of aerosols containing a mixed composition. In that, yes, there was sulfuric acid in the aerosols, that after they got captured, They then did thermally decompose to release SO2 and water. However, these aerosols may also contain other thermally unstable metal sulfates, like ferric sulfates, which is an iron sulfate, and other hydrates that once they got really hot, decompose to release SO2 and then an abundant amount of water. And that allows us to have a different explanation for all of these high water measurements obtained by several different probes. In that this water doesn't represent just vaporous water, but this is a mix of vapor and aerosol phase water. So from here, then I'll say that under this assumption, we then these trends to understand that maybe the LNMS and LGC profiles are not really altitude profiles for gases, but they're thermal decomposition profiles. So that led us to the thought that maybe we need to reanalyze this data using a completely different modality. So instead of looking this as altitude profiles, maybe these are just evolved gas analyses. So to do that, we took this altitude profile for SO2, for example, and turned it on its head. And instead of expressing this against altitude, express SO2 abundances against temperature. So that is what's shown here in this plot. So in this plot, we have the number of SO2 molecules instead of mixing ratio on the y-axis. And on the x-axis, we have the LNMS inlet temperatures, which we were able to extract from project reports we got from different archive sources. Now, these inlets were actually heated to up to about 20 degrees above atmospheric temperatures. And then on the top here, we have the altitude measurement as a reference. So through this transition of going from altitude to LNMS inlet temperatures, what we saw here is that we had two really nicely defined peaks. So then we've realized that these peaks actually nicely fit two different Gauss functions. So we fit these Gauss functions. That's the dotted blue and dotted yellow line. And here is the sum, the red. So the sum Gauss functions fit the data very, very nicely. And from the Gaussian functions, we were able to extract the temperatures of maximum decomposition, or the peak centers. And from all this information, we were able to get peak areas. And peak areas gave us the total number of SO2 molecules released during the thermal decomposition steps. So we did this for SO2. And then for a completion, I'm going to demonstrate that we did this for water. This is the same altitude profile for water, but express the thermal decomposition profile. And note that there's one smaller peak here and a larger peak over there. But if I blow this region up right over here, we see that actually there are several different release steps for water. And so we fit all these different release steps to different Gauss functions. Again, the red line is the sum of all the different peaks. And what we were able to get were different decomposition temperatures, but then we were also able to get peak areas for each different decomposition step, where peak areas gave us the total number of water molecules released from the aerosols. So just as again, for completion's sakes, we did the same thing for O2 and SO3, where some O2 was released during the clog and a ton of O2 and SO3 was released after the clog. Then we did the same thing for FeO+, which we believe arises from the decomposition of ferric oxide. And again, this was after the clog. Now, I'm going to put all this information together over here on the right. On the right is an overlay of these thermal decomposition profiles for SO2, water, O2 and SO3, and ferric oxide. And note that there are several gases that release during the clog, and this is between the temperatures of 75 and 275 degrees, or 50 to 25 kilometers. And these gases included SO2, water, and O2. But then after the clog, and this is the new data that we analyzed, and these are between the temperatures of 275 and approximately 460 degrees, there were several other gases and compounds that released in the LMS. And this included SO2, SO3, water, O2, and Fe2O3, known as ferric oxide. So what does this information mean? To put it all together, we're suggesting that this is the result of aerosols being captured, and these aerosols contain a heterogeneous composition, where these species include sulfuric acid, hydrated ferric sulfate, other uncharacterized hydrates, and a little bit of solution phase water. And then what happened is after these aerosols got captured, they underwent particular thermal decomposition steps shown by these reactions over here with the appropriate stoichiometry. Now, why is this important? Because we see over here that there's two decomposition steps and the release of two different SO2 molecules. And this matches our analysis where we saw the release of SO2 at 220 and 400 degrees. We also see the release of O2. There's two different O2 release steps here, and we see O2 release at least at two different temperatures, 220 and 400 degrees. We also see evidence for iron, where ferric oxide is a thermal decomposition product of ferric sulfates, and this is well known using earth-based literature. And what we're proposing is that once ferric oxide was formed, it flew into the mass spec, underwent electron ionization at 70 eV, and formed these species over here. And we detect the formation of FeO plus as well as O2 above 300 degrees. We also see the formation of several different water release steps, where water is released from the decomposition of sulfuric acid at 185 degrees. We also see the water released from different dehydration steps from ferric sulfate, other uncharacterized hydrates, and the solution phase at several different temperatures. So using this combined information, we have all the number densities for these molecules here. We have the stoichiometry of the reactions, and we're able to work backwards to figure out how much of these parent species were actually in the aerosols. So we took all this information and we subtracted out this water arising from the decomposition of sulfuric acid, and we were able to get estimates of weight percent of these species in the aerosols as well as their mass loading. So this information is then shown here in this pie chart. And you can see that we have three major species: sulfuric acid, ferric sulfate, and water. And if we look at the actual abundances, what we see here is we got really comparable masses of sulfuric acid and ferric sulfates. We have about 22% by weight sulfuric acid and 16% ferric sulfate. But considering the uncertainties, these values are actually quite comparable. So just hold on a minute. Those who are thinking, hey, wait a minute, that's a really low value for sulfuric acid, just give me a moment. Then on the left, we have, I'm sorry, let me back up. What I did not present is that we also in the mass spec saw evidence for the release of magnesium sulfate and sodium sulfate in the mass spec, but we're unable to actually get abundance of this due to a lack of necessary information in the literature, though we're still working on that. But what we do see is there's lots of water, and most of this aerosol phase water comes from the hydrate phase. And why do we say that? Because about 95% of this water that we measured was released between the temperatures of 300 and 460 degrees. And this is consistent with the release of water during the thermal decomposition of minerals such as hydronium jarosite, which is a ferric sulfate, and kieserite, which is magnesium sulfate hydrate. And note that we're getting potentially water released from magnesium sulfate, and we have evidence that magnesium sulfate also released in the LMS. Now, this is the overall picture, like the whole enchilada, if you will. However, if we only look at species released during the clog, for example, only the species that were measured in the original LMS investigations between 15 and 25 kilometers, if we only use those gases with weight percent, relative weight percent. Now, we've assigned this essentially as a volatile fraction of the aerosols. Now, why this is important is that this value is actually right on target with what's estimated by polarimetry and near-infrared spectroscopic measurements, which suggests that the aerosols contain 75% weight percent sulfuric acid, which we believe is a measure of the volatile fraction, not the non-volatile fraction. In other words, the mineral species such as ferric sulfate and magnesium sulfate and others. So with that said, I present you my conclusions. What we are proposing is that aerosols were captured and analyzed by all cloud probes thus far. This includes the Pioneer Venus Large Probe, the Venera probes, and the Vega probes. They all collected aerosols and partially analyzed their contents. For the LMS, our results indicate or suggest that water, sulfuric acid, and iron sulfates are all major aerosol species. It's not that sulfuric acid is the dominant species and everybody else is minor. Actually, all of these are major species. And that most of the aerosol water arises from hydrated iron and magnesium sulfates and some other uncharacterized hydrates. And that what I've not shown is that our aerosol mass loading, but what I did show is that all of our volatile abundances actually match all prior Venus measurements. And I'm happy to share that information with you if you're interested. So then moving forward, we are suggesting that the LMS results illuminate a potential cosmic origin for cloud iron and cloud magnesium. Potentially, these can arise from the surface or from some volcanic activity, but what we think is a little more logical is that iron and magnesium arise from cosmic dust that enters the atmosphere and mixes with sulfuric acid aerosols and forms these ferric sulfate and magnesium sulfate species. What we're also saying and proposing here is that every single direct cloud measurement where every single direct measurement in the clouds indicated high water abundances. And we believe that together all this is important because these present new considerations for cloud chemistry models and especially Venus cloud habitability models. And with that, I thank you for your attention, and I'm definitely open to any questions.
That is great. Thank you so much, Rakesh. Thank you so much, Thérèse, for these wonderful talks and this very interesting, exciting results. So the discussion is open. So anybody wants to go and comment? So we either unmute yourself and comment or just right here. So we have one question here from Michael Way. Thérèse, for Thérèse, refer to the SO2 in one of your maps as a plume. What do you propose the source for this plume is? I know you said you are not sure, but I wanted to ask, assuming it is a plume, then one would obviously not expect a correlation with solar cycle.
In fact, the phenomenon of plume is different from the long-term evolution of the disintegrated amount of SO2. The two things are dissociated. The plumes, they must be the signature of some dynamical motion, and probably we see it in SO2 and not in H2O maps. That's because SO2 is decreasing with altitude. So an emotion will translate more clearly in SO2 than in H2O, if you see what I mean.
I hope that answers the question, Michael. If you want to speak or further questions, thank you. Yes, okay. Okay, then we have another one here in the chat from Mike Cheffin, also for Thérèse. What wavelengths are expected to drive the photochemical variation of SO2 with solar cycle? Are these known to vary in the right amount to drive the observed species variability?
I must say that I have not looked at that in detail. I have just compared, I just took the solar activity as a signature of the UV radiation, but I must say I haven't looked at the photochemistry of SO2 in detail. That's something I have to do. I cannot answer, sorry.
Thanks, Thérèse. Yeah,
Yes,
the reason
go
for the reason for my question was it's somewhat surprising to me. I would expect the molecular species to respond more strongly to MUV input, which is not as variable over the solar cycle as the FUV, which is known to drive upper atmosphere ionosphere variations. So yeah, just wondering what the source of that variability might be and whether it ties into our expectations. But I guess you said that there's some modeling work that suggests
Well,
variability.
I was referring to the paper by Chris Parkinson. It was in 2015, I think. He has made a very complete study of the photochemistry of SO2 and the behavior of SO2 and water together. But
Okay.
I'm not an expert of that, so
I'll check it out. Thank you.
There's a question from Janusz Petowski for Rakesh. A very cool work as always. O2 is also detected by the LNMS, NTLGC, around 52 kilometers. This is before the clock at temperatures much lower than any temperatures where sulfates decompose. Could you comment on that?
That's a good observation, Janusz. Thank you for your question. So yeah, the O2 is a pretty good signal, both in LGC and LNMS. We have either two explanations. One is that there is somehow an abundance of O2 in the clouds that's not yet been detected, but I don't think spectroscopic measurements of the clouds support that assessment. So that leaves the last one is that maybe there are some other types of aerosol species that are extremely thermally unstable, that they were captured by the LNMS and the LGC at around 52 kilometers and immediately decomposed after capture. Now, the inlets for the LNMS were slightly heated, and the LGC had a collection box inside the instrument that was also heated up a little bit. So it's potential that there's some other minor species or semi-minor species that once they got collected did decompose to release O2, but we don't know what those species are. So that's a bit of an unknown right now.
Mike Chaffin, do you want to ask your question on?
I'm interested in, so this is for Rakesh. You said that the iron could be meteoritic iron that was captured in the aerosols. Is the incident flux of, say, iron, magnesium, etc., from expected from meteoritic impacts or dust consistent with the abundance that you observe or retrieve? And
I'd say that we Go
is there
ahead.
a smoking gun that you would look for in some set of future observations to definitively establish that meteoritic source?
So we think the influx is consistent. We are actually working on those numbers right now. There are some estimates of how much iron is coming in, like per tons per day. So we're working on that one and see how much actually needs to come in and how long it needs to stay in the clouds to come up with the abundances that we have. We think that's okay, but right now we have not really fully outlined that one. Then your second question was what was your second question then?
Yeah, so, and I think this ties into the next question in the chat from Alan Tremaine. Um, what is there an observable, say you could measure anything you wanted about the composition of these aerosols? Is there an observable that would tell you definitively that it is meteoritic rather than planetary in
I
origin?
think that the ISRO has a planned instrument that's going to be like a dust analyzer, interplanetary dust particle analyzer. And if they do elemental analysis on that, I think that could be quite definitive, saying there is a lot of iron coming into Venus' atmosphere. With that said, there was also the Pioneer Venus Orbiter ion mass spectrometer. And there is tentative evidence that this mass spectrometer measured Fe plus and magnesium plus in the ionosphere. But
Mhm.
this data was never fully worked up. So that would be really interesting to go back and really kind of work up this data. So I think that it's very reasonable. I think there is some evidence, again, mass spectral evidence from the ionosphere that supports this hypothesis, and that the influx of iron, the tons per day, is also supportive of this hypothesis.
Yeah, we see these meteoritic metals with MAVEN at Mars. And
Right.
the chemistry of the ionosphere is quite similar between the two planets. So
So that's good support for us.
Interesting.
thanks.
And I could actually address Alan's comment. He's asking if there's any way to detect nickel, which will also be quite rich in the interplanetary dust particles. So we actually see some evidence of nickel sulfate, the parent ion, in the mass spec. But nickel sulfates are quite thermally stable, so at the temperatures that the probe experienced, it probably wouldn't decompose and release SO2. So I don't really think that we can see a lot of nickel oxide or things like that, or SO2 arising from nickel sulfate. But we do have some tentative evidence per se that nickel sulfate was measured. The only problem is we don't know what the cross sections for electron ionization are for nickel sulfate, sodium sulfate, magnesium sulfate. So we can't go back from counts, then back to abundances. We'd love to do that, but I am scouring the primary literature for this information right now, matter of fact.
Larry.
So this relates to photochemistry with solar radiation driving the production of sulfuric acid from SO2 and the destruction of SO2. The atmosphere of Venus, being mostly CO2, is opaque to UV radiation below about 2000 angstroms. So the comment is correct that it would be variations in the middle UV that would be driving the photochemistry.
Okay, thank you for the comment.
Okay, another question for Thérèse from Daria Evdokimova. Thank you for the great work. Do you plan to continue your campaign? Well, my question as well, actually. 27 observation runs already.
I plan to continue as long as the Texas instrument is operating. I hope it will continue for long, and younger people will follow what I have been doing. And Emmanuel Marc, in particular, has accepted to take over the database. And also, what I'm aware of the fact that the database hasn't been exploited as much as it could be. As I said, it's a quick look analysis what I have done. so far, what we have done. And it would make sense to use the whole spectral range there are lots of SO2 lines actually which are not used presently. And what we should do is make an automatic retrieval to be able to infer the SO2 vertical profile in each specific case. But this is really a big work. But with Emmanuel, we have plans to try to set up something like that.
In one of your papers, you mentioned earlier papers of the series. You mentioned that you might also be observing from the from the airplane observatory. What is it called? The SX instrument, I think. But that never happened, or
no, it never happened,
okay.
And now it's over, unfortunately.
Okay. Okay, we have a comment from Mikhail Zolotov. Iron over nickel ratio will indicate space sources. Michael Way has a comment. It should be noted that the dust influx is probably not constant unless you are at the minimum or maximum. You are probably well within the bounds. I'm not sure minimum maximum of what exactly, but maybe you want to comment, Michael, on that?
No, I just meant within the min or max bounds of what's coming into the upper atmosphere from the meteoritic infall.
Okay. Okay, so at the moment there's no other comments here. So I'm really curious to see what people think about, we have the chemistry and these observations, and we have these new insights into the cloud particle composition. Is there a way we can relate this? I'm just what Thérèse and team has been observing, and what Rakesh and his team have been finding. How can we connect these?
Well, the SO2 abundances directly relate to sulfuric acid production. So there is that connection there. So how much SO2 is around will definitely impact how much sulfuric acid is made, which then definitely impacts the abundances within the aerosols. So connecting all that, I think, would be very important. And that if SO2 is changing its abundance through some different cycles, then that means sulfuric acid production is also changing. So that maybe the aerosols have different concentrations, and what we're measuring is a range. So kind of outlining that to me would seem important.
Yeah, of course, the probe measured or got clogs a little bit, the 57, what is it, 57, 55 kilometers altitude? 51. So that's a bit lower, maybe two particle scale heights lower than where Thérèse's measurements are, which is more in the 60-kilometer altitude range.
Correct.
You would expect some effect, this whole chemistry and interaction of the cloud particles to have an effect on what you can see from remote sensing, what's happening there in the clouds. And
Martin?
Thérèse.
Yes, I would like to comment. Rakesh, your results are very exciting, very interesting. But I still have a question. That's about the total sulfur budget. The fact that SO2 below the clouds is so abundant, 150 ppm, down to less than 1 ppm above the clouds. And we have seen that H2SO4 by itself cannot explain this difference because the water is only 30 ppm below. So it cannot consume all the sulfur. It seems to me that there must be a reservoir of sulfur. Sulfur must be trapped somewhere in the clouds, in aerosols like, I don't know, S2, S4, this kind of thing. And my question is, if there were SX aerosols, would you be able to say something about them with your instrument?
We have pretty reasonable fits to the data at 32 units, which would be O2 and sulfur. And what I presented was the O2 from those fits. What was not presented is what happened to sulfur. There's an abundant amount of sulfur we get from the clouds. What state it came from is unclear right now. It could be S2, it could be S3. So yeah, I think that there is support for a sulfur reservoir in the clouds as SX. Now, as SX comes into this instrument, it's unclear exactly what it's going to measure. Once it undergoes electron ionization, will we get different fragments or will it all just be S plus? So right now, we only have good evidence for S plus, really weak evidence for anything bigger than that. So I think that you're onto something, and we have some support for that.
Still, of course, we need to explain these surges of SO2 that happen quite suddenly and then disappear also quite fast, within hours. How could that chemically work? What?
Well, I would be tempted to think that it's really a dynamical phenomenon. Some convective motions in the atmosphere, which are easily translated in the SO2 maps because of this strong decrease of SO2 with altitude. And you don't see that. It must happen also in water, but you don't see it because water has a constant mixing ratio. That's what I would think, but I'm not sure it's right. I would like to hear comments about that.
So you think it's mostly dynamics that driving these variations and not chemistry?
That's what I was thinking, yes.
Okay. So a question from Janusz Petowski for Rakesh. Do you see noble gases during the clock? That would also indicate that whatever got released during the clock came from trapped aerosols. To what extent the gases during the clock came from atmospheric gases? I know that CO2 profile indicates the clock, but is the clock total or is there contributions from atmospheric gases during the clock still? Okay. Rakesh, how do you answer?
Most of the noble gas abundances went down during the clog. What complicating this is that overlaying the clog was a different regime of the LNMS, which switched into a noble gas enrichment mode. So this instrument actually measured a bunch of gas at 62 kilometers and sent them to a different part of the mass spectrometer where these gases were purified and enriched to sample the noble gases. And then right around 45 kilometers where the parachute actually was released, the noble gases that were enriched got sent into the mass spec. So there's an overlay of that. But if we erase that one and sort of subtract all that, all the noble gases seem to go down during the clog. And all the atmospheric gas, including N2, go down during the clog. And so what we think is that, yes, there are a little bit of atmospheric gases that are coming in during the clog, but they're very, very low. So for example, the CO2 counts before the clog were, let's say, just under 1 million counts. But then all of a sudden it got 6,000-fold lower. So everything goes down really, really low. And for some reason I have this pop-up thumbs up. I'm not sure where that came from. So really we do think the clog was significant, but as the materials in the inlets began to thermally decompose, then some gases started to come in. And as the gases start coming in, then the noble gases do come up. So we are working with the noble gases. Right now we don't really have any abundances per se for the noble gases in terms of ppm.
Okay, thank you. Aurélien has the hand up, please.
Yes, hello everyone. Question for Rakesh. This is a very, very interesting work. The article was also very nice. Very interesting work for Thérèse. It's a very interesting meeting. I had a question about the bulk aerosol composition, because you mentioned that basically what we observed before was the volatile composition, basically the 80-20% for sulfuric acid and water. And with your new work, I was wondering that the amount of water that was introduced by the hydrate, if I understood well, how does it translate on how much ppmv of water are like stocked into the cloud, and if it reached the limit of 30 ppmv of SO2 that we observed before?
I have not. Thank you for your comment and for the compliments. Very nice. We have not done the calculation to take all the water that's bound in the hydrates and then convert it back to ppm in the atmosphere. We've not really done that. I have a feeling that it may exceed the 30 ppm, but it's not really in the vapor phase. What we're suggesting that it's actually bound up in some type of metal salts or the hydrate phase. So that means there's basically three groups of water. There's the vaporous water, there's the water that's loosely bound in the aerosols that freely equilibrates to the gas phase, and then there's more tightly bound water. So that's what we're suggesting. So it's not necessarily vapor phase. It's actually either partly liquid or partly hydrate phase, which would be much more difficult to see with infrared, especially as the gas molecules absorb much more. So does that answer your question?
Yeah, I guess so, because I was wondering if those hydrates at some point were decomposed thermally, lower down or not, or they kept being bound to the crystal or whatever, or at some
So
point are they released?
I would point to so we also have some suggestion that maybe between 51 and 48 kilometers, there's more vapor phase water than what's been measured. And this is at least partially suggested by these in situ measurements from the Vega, Venera, the LGC, and the Pioneer Venus Large Probe. And maybe there is just a small little band where vapor phase water is actually a little bit higher. And there is a measurement for vapor phase water done by optical spectroscopy in this nice little narrow band. And that was done, I think, in an Ignatieff paper in 1996 and maybe 1997. And they also suggest that water should be about 30 ppm. But from my analysis of the paper, they actually have quite a bit of uncertainty that in their radiative transfer model, the change in irradiance is between 30 and 1000 ppm is very, very small. So we do think that there is some uncertainty in the optical spectroscopy measurements that could suggest that water abundance is in this very, very narrow band, 48 to 51 kilometers, that water vapor abundances are actually higher than 30 ppm, which would then support our analysis that there's some hydrates in these little aerosols that are releasing water a little bit at a time. Hopefully that answers part of your question.
Yeah, sorry, I was mute. Yeah, sorry, I didn't get exactly the reference. If you can share it at some point, but yeah, thank you for your answer.
Sure, I can definitely share the reference with you.
Thank you.
So just to come back, Thérèse thinks it's dynamics. There has to be, which means that there has to be some sulfur like hanging around in the clouds that can then come up by dynamics, but it has to be then in the atmospheric phase, right? So how can we connect that with, I don't know, how can we connect that with the cloud particles that are there? I'm not sure. I'm just trying to think aloud. And Aurélien also wants to say something more. Go ahead.
Yeah, sorry, it's for Thérèse this time. I wanted to be sure because I read the article again. It was a very interesting article that if I understood well, like basically there is no correlation between the measurement of SO2 and the counterpart H2O with every kind of parameters, with the solar cycle, journal cycle.
Yes.
And I wanted to be sure if I understood well at that point.
In fact, what we see on the general plot of the disintegrated abundances of water and SO2, we see that after 2023, the behavior of SO2 is very different. You see it increases on a very short time by a factor of 5, which is enormous. And it goes down on the same short time, 2 months. And this is something you see only after 2023. While previously the variations were much more smoother and could be correlated with solar activity, although I understand what has been said by Larry. But definitely in the variations of SO2 with time, you see a change around 2023. And really, I have no explanation for that.
I was also wondering if the anti-correlation between SO2 and H2O was always present, because that we have a variation of SO2 at the cloud top. I'm not very surprised. SO2 is a long-term species at this altitude, and if there is any variation in the convective layer that may happen and produce some plumes. But I was wondering if every time that you have a measurement of low SO2, you have high H2O, and when you have low SO2,
Martin, I'm not sure you have time to go back to the presentation. You see that, in fact, between 2014 and 2021, you do have a good correlation. We had calculated a coefficient of correlation of 0.9, if I remember, minus 0.9, if I remember well. So indeed, in this case, the anti-correlation, I think, was clear. Now, in 2012, it's not the case. Take the two first points on the left. You see they look correlated, not anti-correlated. But starting after 2014, up to 2022, around that, this was the COVID crisis, the area where we have no data. Here, the anti-correlation seems to me rather clear. And after that, we have water which is more or less constant, except the two last points. And while H2O is rather constant, you see SO2 jumping up and down. And this is really something which is new and which I don't know how to explain.
Yeah, from a photochemistry point of view, it's hard to get your head around. But
okay, I seem to have missed a question. I apologize for that. There's a lot of this.
Yeah, I just responded to Joe Egan, but they asked if the clogs collect all the air size modes, like modes 1, 2, and 3, and do all size modes actually contain the iron sulfates? And would the presence of iron sulfates support the interpretation that mode 3 is crystalline? So given the gap size on the inlets, which are about 0.1 micron or less, we're surmising that any of the mode particles could have got trapped, the smaller ones, the medium size, or the bigger ones. I'm thinking that even the bigger ones could have broken up into smaller pieces and then entered the inlet and clogged it up as well. So I don't know if we can really extract which mode was caught versus which mode was not caught. Regarding the interpretation that the mode 3 has some crystals in it, I think our interpreters definitely support or could support that assessment that these crystalline species in the mode 3 article could be these iron sulfates that once they lose a little bit more water, kind of precipitate out and form a crystal. So we are definitely working on that, and we're also comparing this information with the refractive index values that were measured in the clouds, also by the Pioneer Venus Large Probe. And these refractive index values are actually not 1.44, they're actually much lower than that. And they're actually close to water, they're close to solutions of ferric sulfate. So we're actually working to put all this information together right now. Hopefully, Joe, that answered at least part of your question.
I think.
Yeah, all good. Thank you.
Great. Thank you for all those questions. Okay, so we are at the end of our time slot. If there's any burning questions, I mean, there's 1,000 of them, I know, but for the final one. Okay, David Grinspoon, a moderate-sized airburst impact exploding within or below the main cloud deck can cause a temporary injection of SO2 above the clouds. I guess that's possible.
Yeah, sorry, I have not been able to follow this entirely because the confirmation hearing of Jared Isaacman as the next NASA administrator is going on during this exact hour, and I've had to split my screen a little bit. So I'm sorry if my comments don't completely fit the discussion. I've been watching all the slides and listening to what I could, but I just wanted to point out this is a calculation I've done before, that if you had if you think of Shoemaker-Levy 9 impacting Jupiter, and that sort of polluting of the upper atmosphere that lasted for a while and then dissipated. If you can do the same thing on Venus, because there's a steep gradient of SO2 from below and above the clouds. And so if you have an airburst, a small comet or even just any kind of small impactor that causes a thermal plume, it would pollute the above cloud atmosphere with SO2 for a while. And it's a calculation I've done but never published. And, it really comes down to what is the expectation frequency of a large enough object to do that. And is it a reasonable hypothesis or not? And I don't really know. But the physics works out that the right kind of object would pollute the above cloud atmosphere with SO2 for a while.
So that comes down to dynamics then, Thérèse. Sorry.
That's a very interesting idea. Sure. We should think of it more.
But you would have to really check if that's so the amount of plumes that you see, whether that can make sense in terms of impact, frequency, and location.
That's the question. You can do it if there's the right number of objects of the right size, but is that a reasonable? And that's something that I did some back of the envelope calculations. If Thérèse, if you think it's reasonable, we could try to do it on the front of an envelope and actually see if it works.
Good idea. Thank you, David.
I think there's less room on the front of the envelope. Okay.
Yeah, maybe.
Aurélien.
We need a bigger envelope.
Yeah, exactly. Aurélien.
Yeah, just to it is in the modeling community since Krasnopolsky. We know that if you change the AD diffusivity, the parameter of the convective layer, if you inject a bit more SO2, it can reach the upper cloud very, very quickly, and then it basically dissociate because its chemical lifetime is quite long, and it's in the time scale of a few days. So you don't need per se impact or something. You just maybe only need some variation in the convective layer that could produce this kind of injection. But you need for sure more work on a lower scale model, mesoscale model, and so on.
Okay, thank you very much, everybody. I think we will finish the session today. I hope this format is a good one, that we might repeat in the future. I think there's a lot of work that can be done, maybe collaborations between Rakesh, Thérèse, other teams, to get more of a handle on all these interesting questions.
Well, thank you for having organized this. It's extremely interesting.
Excellent. I'm happy that you enjoyed it. And thank you, everybody, for being here, asking questions, and of course to our speakers.
Thank you, Martin.
Today.
Thank you so much for the invitation and the opportunity.
All right. Okay. And then, sorry, anybody wants to? No.
I just thank you, Martin.
Yes, Sanjay. Yeah.
Sanjay.
No worries. Okay. Thank you very much, and have a great end of your day or beginning of your day, wherever you are. And then see you soon. Okay. Goodbye.
Bye-bye.